Okay, how's it going, guys? This is the second video when determining the rate law of a reaction and the various orders of my reactants. So let's go over a multiple choice problem that's a little bit different than what you may have encountered. Let's take a look at the problem. So we're given a set of data just like last time. Some of them were held constant while the others changed, and we were able to identify the overall change in the rate as a result and determine the orders. But let's look at our multiple choice answers, which I normally don't recommend doing until you solve the problem, but looking at this might be a little insightful. So notice that the orders of the various reactants are kind of weird, meaning that 3 over 2 is 1.5, so that would mean that would have been order of 1.5, which is different than anything we've really encountered. We've only really introduced you to 0, 1, and 2 as various orders. There's a 2.8 here hanging out, and a half order and a half order. We've seen that before, but my point is, our method of using the concentrations falls short when we're given these weird rate laws like this. So instead, this video, I'm going to go over a quantitative way to solve for the various rate orders using the method of initial rates. And if you do it this way, you do get an answer that is pretty much guaranteed to be correct. It does take a little longer than the other method, but I happen to be a fan of this, and if I have the extra time on an exam, I will definitely do this method. So let's get started. So we're given these two different reactants. Let's just solve for the order of the chlorine, because from equation 1 to equation 2, experiment 1 to experiment 2, it looks like I altered the concentration of just the chlorine and kept the other one constant. So let's take a look at these two. So I'm going to call this experiment 1 and experiment 2. So here's the way we do it. Let's do the rate laws for each reaction independently. So the rate of reaction 2 over the rate of reaction 1 is equal to, well, we're just going to be writing the rate laws for them. So K, and in this case, it's carbon monoxide, CO, to the M power. And I have Cl2 to the N power. And that's going to be the same for both of them, right? So that's going to be K as well. And that's going to have the same overall like setting up. So it's going to be M, and that's going to be Cl2 to the N, because they have the same orders. The only thing that's going to change, though, is going to be the concentrations that I add inside of them. So let's fix those, okay? So let's get rid of the insides of these. So because the rate orders equal that, well, my carbon monoxide was 0.25 and 0.25 for both, based off experiment 1 and 2. I'm looking at the data right here. Well, let's look at what also happened from experiment 2 to experiment 1, which, since this one's on top, it's going to be 0.80 and 0.40, as we see here. Now, doing a little bit of algebra, we see that, well, these guys are the same. The K's are the same, and the concentrations and the exponents are the same here, so I can cancel both of these. So this equation simplifies to rate of 2 over the rate of 1 is equal to, that's going to be 0.80 to the nth power to 0.40 to the nth power. Now let's start including some numbers. So the rate of 2 is going to be that 1.97 that I see in row 2. So let's replace that. That's going to be that 1.97, like I said before. That means we can replace rate 1, which was 0.696. Cool. So pretty much now, all I need to do is solve for n. And if we use a little bit of algebra, we can get to where we need to be. So 1.97 over 0.696, well, we can combine these because they both have the same exponent. So we can write it like this. So 0.80 over 0.40 to the nth power is equal to this ratio that we see on the other side of the equal sign. Let's figure out what that ratio is. So 1.97 divided by 0.696 gives me the number, and go to as many decimals as you can in this case, because we want to make sure we're accurate. So 0.28304 equals 0.80 over 0.40 to the nth power. Okay, so Notice this looks pretty similar to what we were doing before. The ratio of the numbers set to the nth power is equal to the rate change that we see here. It's pretty much the same thing, but this is how we derived the previous one. So then how do I solve for n? Well, using our algebra skills again, if I get the natural log of both sides, well, the natural log of 2.8304 is equal to the natural log of 0. Well, let's just simplify this ratio here. 0.8 divided by 0.4 is going to be 2. 0.8 divided by 0.4, you get 2. So it's going to be the natural log of 2 to the nth power. Well, remember that using our algebra skills, that the natural log of x to the n power can be written as this: n times the natural log of x, using the exponent rule. We can bring this thing to the front, this n to the front. So doing that, we can bring it to the front. So we get this new equation Great, we're almost done. How do I solve for n? Divide both sides by the natural log of 2. The natural log of 2. Those guys cancel. So my order for n is equal to the natural log of 2.8304 divided by the natural log of 2. So this is a much more quantitative approach than our previous problem that we did. So now when we solve this, whatever answer we get will be our rate order. So let me get a ratio going as a natural log of 2.83. What do we get? N is equal to 1.501. So going to three significant figures, we get 1.50, which is equal to that 3 over 2 that we were looking at before. So notice that this would have been a pretty interesting one to solve in our previous problem. So what I'm referring to is right here, this part right here, if we were doing this the previous method, right here we would have been a little stumped, because we would have, when is 2.803, what exponent does it need to be raised to give us, what exponent does 2 need to be raised to give us 2.803? And I don't think anybody here would have been able to determine that exponent would have needed to be 1.5. But using this quantitative method, we're able to solve for that rate order seamlessly. So let's take a look at what we did again, and let's solve for the other order, which is going to be the carbon monoxide in this case. So let me squeeze this up because I kind of chewed up all my space in this problem. So I'm going to push it in over here. Okay. But just off the bat, if you see here, you got a 3.3 over 2 as your order for n. If you look up here, you'll see that for your Cl2s, I don't see any other 3 over 2s. So our answer almost certainly is going to be A in this case. So just as a clear reminder, if you saw this ahead of time, that's good. Now let's look at our other one, our carbon monoxide. So let's analyze two different equations. Let's look at equation 1 and equation 2. I mean, rather, well, this would be 3. So using our last example, or way to do it before, we're going to do the rate of 3 over the rate of 1. I'm not going to write all the K's and stuff, because as you saw before, all of the K's and the other reactant that's held constant, those all cancel out. So really all I care about is the one that doesn't, the one that did change, the one that doesn't cancel out. So in this case, the carbon monoxide. So I'm looking at 0.50 to the, we'll call that one M over 0.225 to the M. Great. And that's going to be rate 3 over rate 1, which happens to be 3.94 over 0.696. 0.696. I can combine these into one ratio. Then that's 0.5 divided by 0.25. That's just 2 again, so that's 2 to the M. Now what's 3.94 divided by 0.696? So the answer I get for that is, let's see, so 3.94, 0.696. Oh, look, it seems I made a mistake. So it looks here that for equation 3, it looks like I also doubled the concentration of my Cl2. So I actually made a mistake here that I can't use these two concentrations. What I should have done is I should have used equation 2 and equation 3. So let's actually go back and fix that. So my apologies. Let's fix that really quick. Fortunately, we know the answer is A. So okay, so let's get rid of this 3 here. And let's take a look at equation. Let's get rid of, actually, I'm going to use 3. I'm going to use equation 2 and equation 3. And the reason why is because this changes by a factor of 2x, but this is held the same. Before I was using this one, which was 2x, and that one, which was also 2x. So that's why that was a mistake. Otherwise, our method falls apart, right? Because we need the other one to cancel to solve for this. So let's take a look again. So then what we get is going to be the rate of 3 over the rate of 2 is equal to the concentrations. I'm just going to put them in the same one. That's going to be 0.50 over 0.25 to the m power. And we're left with, we plug in our rates, the 3.94, 1.67 equals 2 to the m. Well, what happens when you divide 3.94 divided by 1.67? Well, you get the answer 3.94 over 1.67, 1.97 rather. We get 2. We have 2 to the m, and then this is just like that previous method we were doing. So what exponent does m need to be to give us 2? Well, m needs to be 1. There we go. So you see, we just learned an extra approach. So whenever, you can set this up the same way we're doing the other way. And that was that, if it's pretty clear, you can see that m needs to be 1 in order for this equation to be correct. Now, if your exponent is difficult to see if you're right, because we didn't actually know what n needed to be for it to equal 2.83. So that's when we need to implement the algebra in order to solve for this rate order. But if there is no need, you're very welcome to then use the other method which we used in the first video, which was just to kind of eyeball it and see what m needed to be to solve for this rate order. So I hope that was helpful. As just a quick reminder, the answer was A in this case because our rate order for carbon monoxide was 1. And there's a kind of an imaginary 1 hanging out here on the top. And then we found out the rate order was 1.5, which is equivalent to 3 over 2 as we see in A here. So I hope this wasn't very helpful. I hope it was, because I found that occasionally on exams you don't really have as clear-cut problems as you do in the review questions, because professors are trying to test your understanding with the material. And I hope this method is helpful in that regard. So next videos we're going to be going over solving the integrated rate laws and various problems surrounding those. So in the meantime, I hope you have a good one and study hard.